All right, so now we're going to look at an actual example of the Black-Scholes model. We're going to use Excel right now. Later on, I'll show you how to do this in VBA. But first, so we've already looked at the model itself. So we're going to look at our first example in this Excel spreadsheet. So here's what we know. We have a 1-year European call option, which of course, if you remember, a call option is the one that gives you the right to buy an asset in the future at a price that's determined today. And we're assuming that this does not pay any dividends because, of course, with the original Black-Scholes model, this was one of the key assumptions. It has a strike price of $50. That's the price at which we're allowed to buy the stock. The 1-year risk-free rate of interest is 2%, and the stock is selling for $52. The volatility is 30% per year. So just a quick reminder, the volatility means is what we can think of as the uncertainty associated with the stock's price, or actually stock's returns is what I should say, because it's not so much the price we're concerned about, it's the rate of return. So this is the uncertainty associated with the stock's rate of return, but specifically the volatility is measured as the standard deviation of the stock's rate of return over time. Okay, so if you wanted to calculate this yourself, you would need to get a time series of data for the stock. You would have a bunch of prices, you would calculate the rates of return, and then you would calculate the standard deviation of those returns. So you would end up with a measure which is normally calculated on an annual basis. Okay, so anyway, whatever that number is, then the larger it is, the more the stock bounces around over time. By the way, we'll see later on that the more volatile the stock is, the more valuable the option will be. Okay, options benefit from volatility, but we'll get to that discussion later in this chapter. Anyway, so here's the information we have. So I put this into a spreadsheet. Um, Here it is, and you can see the stock price is 52, the strike is 50, the risk-free rate is 3%, the volatility or sigma, and what that refers to, of course, is that this is the Greek letter sigma. And then finally, time is 1, which is understood to mean 1 year. And so there's the inputs to the model. Now, these are the intermediate calculations that we'll need. And so those are the D1, D2, and then the corresponding normal probabilities associated with them. So if you remember, the D formula looks like this. Now, where did this come from? Well, that's a very complicated question. We won't have time to get into that right now. Actually, there's a second half to this class. If we run it next year, we can go through here and show where this comes from. But anyway, in the meantime, we'll just use the formula. And so here's D1 and D2. And so we plug in all these numbers. And now in Excel, now this is a very messy formula. And so I just want you to see, if you're not that familiar with Excel, with an actual log of S over X, which is cells B1 over B2, plus the risk-free rate, which is in cell B3, plus a half of the sigma squared, B4. Now this is Excel's, this is how Excel shows exponentiation. This is the caret symbol, which is the Shift-6 key. And then down here, we multiply the whole result by time, which is found here in cell B5. And the denominator, we have B4, which is the volatility again, or sigma, times the square root of t, the time. In Excel, the command for square root is spelled SQRT. So that's our D1. Now, luckily, D2 is a very simple function of D1. And here it is. Just take your D1 and subtract sigma, or this volatility, times the square root of t. Now, remember, the ND1 and ND2, these are probabilities. So in other words, here's what's happening. Here's your standard normal curve. And remember, the mean is 0 and the standard deviation is 1. And so no matter what number n d1 is, d1 is typically positive, by the way. And so n of d1 just simply means take this area to the left of d1, which means this is the probability that our standard normal random variable z is less than or equal to d1. Okay. So you can think of it as an area under the curve or a probability because it means the same thing. And of course, that means that D2 is always smaller than D1. And sometimes it's negative. I don't think it is it here. Um, no, not this time. It's very close, but it's not negative. Let's say it's here. Okay, so those are both probabilities. Now, the important detail here is that each one of these is therefore bounded between 0 and 1. Because there are probabilities. And we've also mentioned how we can interpret these. This one, which you see here, once we calculate it, ND1 is approximately 0.6358. And the command in Excel for that is norm.s.dist. Norm for normal, S for standard, dist for distribution. And then the values we want to be 7, which is D1. The 1 there tells us that it's a cumulative probability, which is what we need. So this is how Excel calculates these cumulative probabilities for the standard normal distribution. And so this tells me, let's round it to 6359. That means that if the price of the stock goes up by $1, um, all right, sometimes it's very stubborn here. So what that basically means that if S rises by $1, S2 will rise by approximately 63.59 cents. And vice versa, of course, if S goes down by $1, then you'd also expect the call price to fall by approximately 0.6359 or 63.59 cents. And the ND2, which in this case is 0.52189, you could think of it as the approximate probability that the call will finish in the money. In other words, the stock price will exceed strike price at maturity so that the option have a positive payoff. Okay. It doesn't guarantee you'll have a profit because if the payoff is less than the cost of the option, we'll still lose money. But being in money means that at the end of the maturity date of this option, the stock price in this case exceeds the strike price, which in fact you can see here right now, this option is said to be in the money by $2. So this is the probability, approximately, that the option will, at the end of its lifetime in 1 year, will actually finish in the money. Okay, so now with all that's being said, what we have to do is apply the Black-Scholes formula. Now, let's go grab that one. And here it is. This is actually the simplest part. Let's move this up here somewhere. And so you can see now once these intermediate parts are done, the call price is actually straightforward because you have S times ND1. The stock price is multiplied by, and the stock price is way up here, by the way, B1 times B9, which is ND1. Now, for the second part of this formula, we have X e to the minus RT. Think of this as the present value of X dollars. In other words, that number that you're seeing there is less than X. That tells me how much I would have to save right now to have X dollars at time T when the interest rate is R. So the command in Excel for that is a little bit tricky. It's EXP. EXP is E raised to that power that's in the parentheses. So we need to have EXP XE to the minus RT. This is R. This is T. It's negative, as you see. EXP means E raised to that power times X. And then at the end here, if you notice, that gets multiplied by ND2. So that's what this B10 is. And that's our call price. So it looks surprisingly simple considering how much math is going on behind the scenes. I mean, it is a very complicated derivation to say the least. But once it's done, the model itself isn't really all that complicated. So that's our call price. Now, this call price is the only one that is consistent with no arbitrage opportunities. So we said that the Black-Scholes model is a new arbitrage relationship. Since the resulting price, the old one, at which there are no arbitrage opportunities. So a lot of the results in option pricing theory are derived this way by showing what has to hold to avoid arbitrage, and then maybe explaining how the arbitrage would work if we in fact did have a violation here. Now, by the way, later on in the section, we're going to go back to revisit Pocal parity, and we're going to actually show how to prove it. Oh, all right. Well, okay, I just realized it's in a different section, but I'm going to show it to you anyway. I want you to see how we can determine if a relationship is indeed a no arbitrage relationship. And the logic behind that is that a relationship can be shown to be a no arbitrage relationship if we can prove that two positions with equal risk and same true cash flows have the same price. So that's kind of the logic which all of this is predicated. So imagine yourself with two portfolios of assets. So you have to visualize it's a large box that's full of some kind of assets, stocks, bonds, interest rates, whatever. And so what we need to be able to do to show the lack of arbitrage opportunities is that if we assume that each of these generates the same cash flows in the future, same timing, same everything, same size, as long as they generate the exact same cash flows. And then, of course, assuming that there isn't a huge difference in the risk between them, what we have to do, we can conclude that the prices of these portfolios must be the same today to avoid an arbitrage. All right, so in other words, let's just say that P1 is the price of portfolio one. And of course, that means P2 is the price of portfolio two. And if we decide if P1 is greater than P2, and now keep in mind what that means. You've got two sets of assets that provide the exact same cash flows in the future with the same level of risk. Then what you would do, you would buy assets in portfolio two. Actually, I'm using that for the price. Let me change that a little. Um, and then they would sell or take a short position in the assets in portfolio one. Now, of course, we're assuming that it's possible to do that. If these are traders at major investment banks, they shouldn't have any difficulty short selling any assets in the economy. And so what this is going to do is the cash flows today. You're paying for portfolio two, you're short selling. Oh, I just realized this is not right. Sorry, this is portfolio one. The net cash flow, I'm collecting P1 because I'm selling its assets, but I'm paying P2 because I'm buying those assets. So the net cash flow is P1 minus P2, but because we're assuming P1 is greater than P2, that implies that this is positive. And then what about in the future? Let's assume that these cash flows take place 1 year in the future, just to keep it simple. Call it future. Okay. In the future, at time t, whatever that is, we have both a long position in the exact same cash flows. Okay? In other words, if we bought portfolio two, and we're collecting these cash flows and we're paying these out because we sold those assets, but they're identical to each other. So the net effect is that we have no cash flows in the future. So our net cash flows in the future equals zero. Now, so here's the bottom line. We have been able to put cash in our pockets today with no future outflows. Now that's kind of interesting. We're able to somehow put money in our pocket now without any future exposure. And so that would be possible in an efficient market. So this is an arbitrage opportunity, or simply an arbitrage. It's often just called an arbitrage. Hull's book just calls it an arbitrage. And so this can only take place when markets are inefficient. And in this case, we know that they are. The two portfolio prices have been identical in a perfectly efficient market. And so none of this could have happened. Now, of course, if instead P1 is less than P2, we can just reverse all of this. Let me make a small change here. Um, and then I just have to reverse the two. Here where this becomes sell and this becomes buy. Remember, the whole logic behind this is you're selling whatever is relatively overpriced, and you're buying the undervalued or underpriced asset. And that's how you make your arbitrage profits. And so then, this whole chart would be reversed. So you're collecting P2, and you're paying P1. But now, of course, we're reversing the two, but now the assumption is different. So now this time it's P2 minus P1 that's positive, and there's your arbitrage. Okay. All right, great. So this is also an arbitrage. So therefore, here's our conclusion. Since both lead to an arbitrage opportunity, only at P1 equals P2 can arbitrage be avoided. Now, of course, this is how these types of proofs tend to proceed. You're taking two cash flows and setting them up to ensure that they have the same cash flows in the future, but different prices today, and we can see how that would result in an arbitrage, which leads us to conclude that the prices must be the same today because that's the only way we can avoid an arbitrage. So we'll see more of this as we go along. Now, of course, we're making assumptions here, but certainly hedge funds can jump in on the bandwagon and exploit these types of opportunities. As you know, hedge funds are these basically they're organizations that are set up to gamble with rich people's money. I mean, what else can you say? And they have invested enormous quantities of money in the most powerful and sophisticated computers in the market, and have access to the vastest information about prices. And so they program the computers to watch massive data. And the minute they recognize an arbitrage opportunity, even if it only lasts for a fraction of a second, the computer is actually programmed in advance to jump in and actually execute orders to take advantage of the arbitrage. So the fact that this can happen, the fact that it's possible for these computers to detect these discrepancies as soon as they happen and to jump in and take advantage of them, that means that if these opportunities arise, they may only last for fractions of a second before they will be corrected by the buying and selling of programs that are set up to find arbitrage. So that basically means that for all practical purposes, prices will stay in alignment pretty much all the time. And if they don't, the problem will disappear so quickly that human beings won't even notice it. So that's how we know that markets are super efficient. Although of course they're never going to be perfect, but the fact that this kind of thing can happen instantaneously using computers means that any discrepancies will be corrected almost immediately. Okay, within like nanoseconds, that kind of thing. So, in other words, there used to be jobs on Wall Street for people who were called arbitrageurs. They were there just to look around and look for opportunities, but that really doesn't make any sense anymore. But anyway, so with the Black-Scholes model itself falls in the category of a no arbitrage model, meaning that if the price is different, you can demonstrate how arbitrage opportunities would result. In fact, all derivative pricing models ultimately are no arbitrage relationships. All right, now, let's see, where are we? I lost my place. Oh, yeah, so here I rounded to 764, where you can see this is what we did in Excel. Now, here's the put. Now, I did mention the other day, I think, that the original Black-Scholes model was not set up to price puts. Now, keep in mind, these guys are not trying to invent some, like spectacularly successful software or something like that. These are academics pursuing this idea that we could come up with a model to price options. So they just wanted to show us the basic framework that could be used to do this. That's why it took a while to get to the other things like puts and options on assets that do have cash flows, and eventually American style options, because it's all academic research. Now, the software that is being used to implement Black-Scholes is probably proprietary, but the actual model itself, it's something produced by academics for the benefit of humanity. So their job was not to make the model lucrative, I guess, but to make it clear to everybody what it was doing to help them understand how option pricing works. So they didn't see anything wrong with issuing or writing a paper about the Black-Scholes model when there was no mechanism for pricing puts, because later on researchers were able to show how we would do that with this relationship called hook-wall parity. So hook-wall parity can be used to demonstrate or show the correct or arbitrage-free price European put um, written on a non-dividend asset, or an asset that has no cash flows. But since these are stocks, this means a non-dividend asset from the price of the corresponding European call option. So the first thing about this call, you first have to use it to come up with the European call price. Then you can flip it around into a European put price. Later on, it was shown how to just sell for the put price directly. So here's what this thing looks like. All right, so it's a pretty straightforward idea. Just copy this. Okay. And you can see you recognize all these variables. Put P is the European put price. C is the European call price. S is the strike price. R is the risk-free rate with interest. Um, well, E is the constant 2.782, you know that one. And then finally, S is the asset price, which is in this case is a stock. Oh, I forgot about T. T is time measured in years. So they're claiming here that if I know the C, the call price that came from the Black-Scholes model, all I have to do is add the present value of the strike, subtract the stock price, and I'm all set. There's my European put price. So the question is why? Where did this formula come from? All right, well, guess what? I'm going to show you right now, even though it'll come up later in the notes, but I want you to see it right now. Um, this can be demonstrated as follows. So here's what we have to do. We have to set up two portfolios, and let's call them portfolio A and B. So portfolio A will be the put and the stock. Portfolio B will be the call. Now, this is the interesting one. What you've got here can be thought of as a treasury bill with face value X and maturity T. Now, we have to assume that such a thing actually exists in the market, but the idea here is a treasury bill is what we call a zero coupon bond, which means it's sold at a discount from its face value. And what's actually happening is the investor is paying a discounted price, but receiving the full face value maturity. And what they're actually earning is what's called a capital gain instead of explicit interest payments. So the zero coupon bond, as it's called, is one where bond is sold at a discount the face value, which in this case, well, it could be anything, but here we're assuming that it's equal to the strike price of the two options. Um, so that the investor earns a capital gain equal to the difference between the face value and the price of the bond. So the zero coupon bond, the maturity of 1 year, a face value of $1,000, and a market price. Um, Actually, let me phrase this a tiny bit. Has a market price. Let's just keep it simple. Let's just say 950. Then, well, you can see what's going to happen here. The investor pays $950 today and receives $1,000 in mirror. This means that he or she has earned a capital gain of $50. Okay. So that's what's happening here. In other words, this X e to the minus RT is assuming that this is what's happening. It's a treasury bill. It just so happens to have the same face value as the strike price of the two options. We're assuming that this thing exists. And so that way we can think of that as an asset. Essentially a treasury bill with a face value of X that matures at time T. Now, just in case I didn't mention this before, this relationship, this so-called parity relationship, assumes that the call and the put are European, of course. Um, they are both um, written on the same asset, in this case, stock, have the same maturity and the same strike price X. Right, I should have put in the symbols here. S, let's give this thing a minute. I don't know why my word is horribly slow tonight. S, same asset, the same maturity T, the same strike price. Okay, without that, then none of this works, by the way. All right, now, here's the question. Why does this relationship hold? Well, here's my two portfolios. So what I'm going to do is set up a little table here. So what exactly is going on here? So I just want to introduce some new notation here. Just to make it clear, I'm going to use the letter capital T to represent the maturity date of these two options. So in other words, S will represent today's stock price. But when I add that subscript, ST, it becomes the stock price at time T, meaning at the maturity date of the two options. All right, now that's a huge deal because that's the date on which we can show what their cash flows are going to be. These are European options. They only can be exercised on the maturity date, which is capital T. So that's the relevant date for these cash flows. Now, here you're seeing two different scenarios. In the first case, the stock price ends up less than X. In the second case, clearly it's greater than or equal to. So there's really only the two scenarios we have to consider. No matter what happens, one of these has to be true, right? And so we don't have to be any more precise than this. So in the first scenario, ST is less than X. The put will be exercised and will provide us with a payoff of, and then the stock price is ST. We don't know what that is, but it doesn't matter. It's ST. And that leaves us with a net position of X. Now, for the B portfolio, the call expires without being exercised, but X is guaranteed, the treasury bill is guaranteed to be worth X dollars. Now, in the second scenario, is the put that's not exercised. Stock is simply worth ST. And down here with portfolio B, the call is exercised, providing a payoff of ST minus X and zero. Actually, ST minus X. We don't have to worry about the zero because by assumption, this is a non-negative number. And then the strike price here gives us a total position of ST. Now, what did this just prove? Well, if you look carefully, you'll notice that no matter what scenario takes place, the two portfolios have the same cash flow. In other words, in the first case, portfolio A and B are both worth X dollars. In the second case, they're both worth ST dollars. So in other words, what we just proved is that future cash flows, both portfolios will be identical at time t. Therefore, the prices of the portfolios must be equal today in order to avoid an arbitrage opportunity. And so therefore, by saying that the prices are equal, that implies that P plus S, which is today's price or value of this portfolio, equals C plus XE to the minus RT. And with a little bit of algebraic rearrangement, we end up with, and there you go. There's our book called parity condition. Well, this is something you don't see in other disciplines. This is not how proofs normally proceed in math. I mean, it's a little bit different. Okay, let's put it that way. We're appealing to this idea of arbitrage and the fact that if there is an arbitrage, market prices will adjust until the arbitrage disappears. So that means that in principle, this relationship has to hold in practice. All right. So there's our book called parity condition. That's where it comes from. It's all enforced by this idea of no arbitrage. Beautiful. So what were we doing before? Well, we're building up to the Black-Scholes model. Specifically, we'd already priced a call option with Black-Scholes. We wanted to know where this came from. And the answer is book call parity. So based on book call parity, actually, it turns out that I just mentioned this in passing here. Um, the book call parity condition can be combined with the Black-Scholes model to come up with a formula where the price of a European put can be solved directly without going through call parity. In other words, we don't need to know the price of the corresponding. European call option. So that's I believe that's in the slides too. Let me just go see where I put it. If not here, it would certainly be another section. All right, so I guess it comes up later, but what this formula is here, based on the Excel information, is C plus X e to the minus RT minus S. So this is clearly the Pocal parity one. Okay. The second one is the one I just mentioned that you can actually derive it from Black-Scholes. But you see, there's the problem. It does require these two new terms, n of negative D1 and n of negative D2. So it's there if you want it. And it looks like this. It's kind of a mess. Um, X, I made a bit of a mess here. Okay. X to the RT times n of negative D2. Let me just neaten that up a bit. And then you'll have plus S n of negative D1. So that this way you can take it from directly from Black-Scholes. You don't need C here, but the formula is kind of a mess. But here, this one is Pocal parity. The first one, the second one is this version that comes from substituting Pocal parity directly into the Black-Scholes model. So you can use either one. All right. So now the question is, what happens when we do suddenly have options written on, let's say, stocks that provide a cash flow to the owner? Now, all of this really makes it possible to price a much larger variety of call options because it means the asset itself can have any cash flow that is necessary. So you can have, for example, currencies where we can earn the foreign rate of interest, bonds which provide interest payments, stock indices that may provide dividends. So in other words, this is really a huge deal because suddenly we're opening up the universe of calls that we can price with Black-Scholes. This, by the way, is the work of Robert Merton. Okay, he's the one who came along and said, listen, the model's fine as far as it goes, but we would like to extend it out to other types of options as well and make it really useful. Okay, so it turns out, though, that we have to be careful here because we have a model that has continuously compounded interest rates built into it. And the cash flows from some assets do not really follow along with continuous compounding. So this one can be a bit of a stretch sometimes. It depends on what the asset is underlying the call of the put. So we have to be cautious with it. But if the asset's cash flows can be modeled as a continuously compounded rate, well, that makes things a lot easier because then what we're going to do is create this variable Q. And Q will represent the continuously compounded return, which remember, continuously compounded means that the number of compounding periods per year is infinite. So Q is the continuously compounded yield or return to the underlying asset. Now we'll see that there are some cases where this type of assumption cannot be justified, and there'll be a separate formula of that. But when we can at least approximate the returns to an asset as a continuously compounded rate of return, then what we're about to see will hold. And so you'd be surprised how little change there will be. You might think we have to almost start all over again, but in reality, there's only a handful of changes. For one thing here, so wherever there used to be just plain S, there's now SE to the minus QT. We could think of this to be adjusted actions, or Hull likes to call it the Burton model. Sometimes he calls it the Black-Scholes-Merton model. I think he doesn't want Merton to get stiff for credit. As long as it's clear that it's not the original Black-Scholes. All right, so there's only one difference, and that's here. But we still have to look at D1 and D2. There's a change to D1. Yeah, it's having a slow night. So I just wanted you to notice there's only one change here. D2 does not have any changes. It's the same thing. Oops, no, so let's not go there. Yeah, D2, whoops. Oh, it just says that here, D2 is unchanged. So it's surprising what a big difference it makes. Just those two little changes. Although I'm going to mention it up front, I haven't quite got to there yet, but it turns out the Pocock parity condition also was affected. So I'll mention that right here. And basically it's the same thing. We have to adjust the S to take into account the yield that the asset is providing. And so the new one becomes it's a little bit further down. Let me just go get it. Here we go. And you'll see that it's the same thing. The S became S e to the Q or T, or the QT rather. And that's the only change. Wow. So Merton, he really extended the reach of the Black-Scholes model quite a bit here. It's, especially after Pocock parity became available. Right now, at this point in history, it's possible to price virtually any option as long as it's a European call or put, um, because we have this extension that makes it possible to price it on anything. But again, it's only going to work for European calls and European puts. The American models had to come later. And they unfortunately are unlike these, which are nice solutions to formulas. Um, those require numerical methods where there's a lot of time going on. There's a lot of steps. There's a lot of calculations. It's really a very complicated process because we have to allow for a decision at every point in time whether it makes sense to exercise the option prior to the maturity date. Here we don't have to deal with that. The only time we get to exercise the option is on the actual maturity date. And the model, the Black-Scholes model, by the way, doesn't explicitly show us anything in between today and the maturity date of the option. It goes directly from one to the other. Whereas the American option pricing models that we'll see, it shows every point in time from today out until the maturity date of the option. And at every one of those points, we have the ability to say, does it make sense to exercise early or not? So yes, it gets a bit much, but these are nice formulas that we can solve for directly. Okay, now, um, so what's coming next is another example, this time where there's a dividend yield of some kind. And so here we've got a $30 stock with a continuously compounded dividend yield of 3%. The risk-free rate is 5%. What's the Black-Scholes price of this European call with a 6-month maturity and a strike of 28? So this is spreadsheet number 2. Here it is. And you can see all these numbers have been put in there. And so, what you're seeing here are the new formulas that we just showed. The ends are just, again, the normal probabilities. And then here we're using the new, or let's call it the adjusted Black-Scholes model to come up with a price of just a hair under $3. And down here, we can again approach this in 2 different ways. We can either use the adjusted put call parity formula or the approach I showed you earlier, which involves substituting put call parity into Black-Scholes. So yeah, this turns out to be approximately $3 for the call. The put with the adjusted put call parity is about 72 cents. By the way, there's a little trick I'm going to show you right now with Excel. If you want to see all the formulas at once, ooh, that was cool. What in the world did I just do? Well, I'll tell you, I'll let you in on the secret. This is an Excel tip. Excel spreadsheet at once. You use control. And by the way, this is the same on both the Mac and the PC, which is very unusual. Now, what is that symbol there? And where is it found on the keyboard? This is called tilde. Never see it in English ever. Um, it is found on the key to the left of the one. It's been there your whole life. You never noticed it. Take a look. There it is. It's the shift capital on this key right here. God only knows what it's doing there, but it's got tilde. If you hit shift and then that button, actually, if you do it with the control, you don't need to bother. Just control and that tilde button. So what will happen is it'll show you the formulas to return to the original format. The same thing. So you can toggle back and forth between them. All right. So this is Section 6A, actually, this is a fairly long chapter, or, well, it's not, well, maybe it's a little deceiving because what we're going to do next is actually look at the Greeks. But before we do that, the next time we meet, I would like to finally introduce you to some VBAs so I can show you how to take the Black-Scholes code and turn it into VBA. And then you can write some programs to check out the prices of different models, sorry, different options. So we want to do that as soon as possible because, of course, we only have so much time in this semester. And then we'll quickly run through the Greeks. And then I'd like to show you the more advanced option pricing models, specifically the ones that are meant to price American options. And then at the end, we're going to look at a technique that's designed to price what are called exotic options, which are much more complicated. And so we'll be using statistics essentially to come up with the prices of these options. Sadly, there's not enough time to do that right now, so we'll leave it here. But next time, we'll start to look at VBA, learn how to use it, where is it located in Excel, and we'll do some very simple programs and to get a feel for it. And then we'll have one or two assignments, and then we'll keep going on with the new material. And then I think the course ends on the 15th, but I can continue to give you time for a few days after that for whatever assignments we have. So we don't want to rush this too much, but sadly we only have really another week or so. So I want to continue giving you all this good material, but we do have to have at least one or two assignments. So the next thing we'll do is some basic VBA so you can get it started on that. All right, so let's see you all next time.